with you a video which is mostly explained by the Srinivas sir. So he will briefly describe about that particular experiment and about its little bit of theoretical background as well as its basic construction of that experiment. You can go through that one at the same time in the class also. What we will do is that we'll briefly look into the experimental setup of that particular experiment, and if time permits also necessary, then we'll go through the little bit of theoretical background for that particular experiment. Most probably almost all the theory that is necessary for doing all these experiments or for understanding these experiments you're going to learn in the heat transfer course. So after going through that brief explanation, we'll take the attendance as usual. And the TAs, one is Vishnuvardhan Reddy and other TA is Raj Kumar. They will be yeah, uh, they will be giving you the data for that particular week experiment, and based on that data, you can write the report and submit to the TAs. They will give you the guidelines what they are expecting in that particular report, and you can submit that report by the next week. Okay, and as there will be marks for day-to-day evaluation, that means those who haven't attended the lab will lose some marks for that particular component. Just please take a note of it. Please take a strong note of it. Okay? So please do join the lab session for that brief period of time where we'll have some brief discussion on the experiment and mark yourself present. That is concerning the, let us say, the explanation as well as the report writing part. So what exactly they are expecting from your report, the TS will give you the guidelines. And in this particular laboratory, we'll have most of the experiments are concerning the heat transfer, and some of the experiments are concerning the fuels. Okay. Most probably fuels has about 2 to 3 uh, experiments, and most of the other things are based on the heat transfer ideas. As for the evolution, your day-to-day evolution, that means class attendance as well as the report writing has, I will let you know about the exact percentages. That is the one component, and the other 3 components are, there will be one quiz based on the experiments that are being finished up to that point. It will be MCQ type quiz, and there will be one more quiz after your mid exam. Those 2 quizzes will carry some marks. At the end, there will be one end exam. So in the later classes, I will let you know the distribution, but these are the 4 components that will contribute to your final total. Okay. As for the today's experiment, today we are going to, I'll just briefly show you the same video. Later onwards, you can also watch that video, as because we are going through the pandemic again, probably you may not be able to do these experiments by yourself. If time permits or if things settle down, then there will be an opportunity to do them by yourself. So what is the objective of this experiment is to evaluate experimentally the equivalent thermal resistance of a composite slab. Where do we find such type of applications is that, for example, the door of a refrigerator or a boiler valve. where there are multiple layers of materials with different thermal conductivities are being stacked in the parallel direction or in the perpendicular direction. Yeah, in the perpendicular directions. In this particular experiment, we are considering three discs, which is of made of metal and then bakelite and then pressed steel. So cylindrical, all these three discs compose the composite wall. And what are the other things that we have in this particular experiment is that all these three discs has the same diameter and same thickness also. And at the center here, exactly where the pencil is pointing, here there is a electrical resistance type heater located in between the aluminum plates. On top of the aluminum plates, there are, as I was mentioning, three cylindrical discs. These are mild steel one, then bakelite, and then pressed wood. We have similar type of discs at the bottom of these aluminum plates also. And between these aluminum plates, there is a electrical resistance heater, and between these each plate, there is a thermocouple located to obtain the or to calculate the temperature at that particular location. There are four thermocouples here at the top. At the same time, there are four thermocouples located here. So one thermocouple is at the top of the mild steel plate, and the other one is in between the mild steel plate and bakelite, and the other one is in between bakelite and the pressed steel. And finally, the fourth one is between the aluminum plate and the pressed wood. This is the, let us say, the construction of the composite slab. Then this entire thing is placed in a enclosure so that the heat transfer from the composite slab to the atmospheric air is minimized due to the convection. At the same time, at the temperatures for which we are considering, the radiation from the composite slab is minimal, as the temperature we are most probably considering in the range of about 100 degrees Celsius. And now there are let us see the other components of this particular experiment. This is a small hand press. By using this small hand press, we can reduce the contact resistance between the different components in the composite slab. Just by pressing it, we can reduce the primarily the contact resistance between all these three different plates. And this is the dimmer stat by using which we can control the power input to the heater. By appropriately tuning this one, we can select the what is the voltage given as well as the current passing through the heater, so that we know how much amount of heat is given as an input here. And by using this multi-channel temperature indicator, we can note down the temperatures measured by the thermocouples at all these 8 locations. We can find out the by rotating this particular knob, we can find out the temperature measured by the each thermocouple. So these are the all three knobs that we can use. How this experiment will be done is that uh, we tighten this hand press, and then we'll move this dimmer start to 0 position, and then we turn on the power, and then we gradually increase the dimmer start press so that we can appropriately select the voltage as well as the current, so that we know what is the amount of heat that is being given in the heater. And also we have placed these composite slabs, equal composite slabs at the top and bottom also. So we consider that half of the amount of energy is flowing towards the top as well as the towards the bottom. Here, as you can see, sir has ensured that the this is switched on, then both are at the zero, and then slowly it is moved to increase the voltage, and then at 80 degrees sir has stopped, and then sir is considering that 80 volts as well as the 5 amperes is the 0.05 amperes is the input to the heater. By multiplying the voltage with current, we can find out the heat input here. And after that, by rotating this knob, we can note down the temperatures at all the 8 locations. What we do is that we switch on the experiment and we note down the all the 8 temperature readings, and we wait for some time, and after 10 minutes we note down the next set of readings. Similarly, for every 10 minutes we note down the new set of readings. When there is no significant change between the two set of readings, we can consider that the system has reached the steady state, and we can use those final set of readings in the calculation of evolution of the total thermal conductor, total equivalent thermal resistance. Yeah, you can go through the video again. Now let us briefly see the calculation of the what quantities needs to be calculated from the this particular experiment, assuming that you have done the experiment. So these are the dimensions of the components that are involved in the experiment. These are the diameter of the slabs. Each one is zero point 0.3 meters, and there are three types of metals are being used. One is the mild steel, bakelite, and pressed wood. This is the thickness of the each slab, and this is the range of the mica heater, and this is the range like uh, these are the ranges for the three other components. Those are the dimmer volt and ammeter. And using the multi-channel digital temperature indicator, you can find out the temperature between 0 to 300 degrees Celsius. As I was mentioning, we first ensure that we have applied enough pressure so that the contact resistance between the different slabs is minimal, and we keep the dimmer stat at zero position before we turn on the power supply. Once the power supply is switched on, then we adjust the dimmer stat for a required amount of heat input by increasing the voltage gradually. After doing that one, we take down the thermocouple readings, that is 1 to 8 for every 10 minutes. And once the system has reached the steady state, then we'll turn the dimmer stat to zero output and then switch off the main power supply. And we have finished the particular experiment. Let us see how the calculations needs to be done. So these are the readings that one is to take if we do the experiment. We'll note down the voltmeter reading. So we're adjusting the dimmer stat for some particular power input. So we'll note down that voltmeter reading as well as ammeter reading. By product of voltage and I gives the power input, and then we'll note down the temperature readings, 8 thermocouple readings for every 10 minutes. Based on the input given here, the system will reach a steady state after some time. Then what we are doing is that we are calculating 8 temperature readings. We'll use the T1 plus T2 as we are having symmetrical composite slabs on the both sides of the heater, and we are measuring the temperature at uh, four locations. We can simply average them at the same places, which corresponds to the same location on the both sides. So that first one will be T1 plus T2 gives the one temperature, and T7 plus T8 gives the another temperature. And as you know, the thermal resistance is equal to the driving potential divided by the heat transfer rate. So this is the common definition for the thermal resistance. A similar thing can also be used for electrical resistance also, or even for resistance to the mass transfer. In all the cases, at the numerator, you have the driving potential for heat transfer. Temperature difference is the driving potential. And at the bottom, you have the transfer rate. In this particular case, we are dealing with heat transfer. At the bottom, we'll put the heat transfer rate, that is Q. As we know, the amount of heat is given, that is the heat transfer rate, from the V multiplied by I divided by 2. The reason why we are using 2 here is that half of the heat flows towards the top of the composite slab and the remaining half flows to the bottom. So this is the assumption that we are making by having the symmetrical composite slabs on top of the heater as well as on the bottom of the heater. Based on that assumption, we know the Q1, that is the heat transfer rate, and we have measured the temperature of the surface at the top as well as at the bottom. So these are the two temperatures among the four that we are measuring. Now we know the delta T, this is the temperature difference divided by the heat transfer rate. We can substitute these two quantities, then we can find out the equivalent thermal resistance of a composite wall experimentally. Now we can cross check whether the experimentally measured value is how far accurate if we compare it within terms of the theoretically obtained value. This is the equivalent thermal resistance. If we write in terms of summation of the thermal resistance for each slab, here Kms is the thermal conductivity of the mild steel, Kb is the thermal conductivity of the bakelite, and Kpw is the thermal conductivity of the pressed wood. L is the length and A is the area. As the dimensions of the slab are known, as well as the thickness and the diameter are known, then we can use these, all this information is given here. The geometrical details are given here. At the same time, the thermal conductivity of the three materials that are being used in the experiment are also given here. Now we can substitute these quantities here. L is the thickness of the slab here, and A is the uh, surface area from the diameter of the slab. We can substitute these quantities and we can find out the equivalent thermal resistance from theory. Now we can compare what is the error due to the like difference between the theoretically obtained value as well as the experimentally obtained value. This is the final comment that you can make based on the both those readings. Yeah, okay. That's all for about this experiment. Please go through the video that I have shared uh, to familiarize yourself with how this particular experiment will be done. Okay, a bit more in detail. Okay, now we'll take the attendance. Vishnuvardhan Reddy, can you please?
Yes, sir. I'm here.
Yeah, please take the attendance.
Okay, sir. I will take it. Yeah. How many roll numbers are there, sir? From 1 to
CR can respond.
88 students.
88. Okay. Okay, roll number 1,
Present, sir.
2,
Present, sir.
3,
Present, sir.
4.
Present,
After
sir.
Share.
calling them, I will directly take the attendance from there itself.
Okay, sure. If it works,
From
yeah,
next
no
class
problem.
onwards,
Yeah, yeah.
yeah, students, I will take the attendance from the here in the people. Your roll number and names are displayed, right? Please ensure that your roll number underscore name is there in the displaying name. Okay,
Okay.
I will take directly from there instead of calling. I will
Okay.
take at any time between 2 to 2:30. Okay, be ensure that.
Okay, and just before closing this one, I just want to add a couple of points. These are not relevant to this particular experiment. Those who might have some interest towards the thermal conductivity of materials can find them pretty interesting. Okay, can you think of any possible way to control the thermal conductivity of a material without changing the composition? There is one interesting aspect is that you can control the conductivity of a material. Particularly, these aspects are quite important in the nanoscale. So as soon as you attach different types of materials together, even there is a perfect contact between them. So if you think even at the molecular level, if you put together all the atoms of different molecule very nicely packed with each other, still there will be a thermal boundary resistance. That's one point. And the other possible way to control the thermal conductivity of a material without changing its composition is by having the grain boundaries. By having the grain boundaries in the material, here we are only ensuring that molecularly we are tuning the boundaries, but the chemical composition of the material does not change. Okay, by having such type of grain boundaries, we can control the thermal conductivity. That's just one point. And also the other point which I just want to mention is that I was mentioning that if you add multiple materials, like even if you perfectly stack them at the molecular level, either it could be two solids or it could be multiple solids or a solid and liquid, there is always a resistance between the resistance for the heat to conduct from one material to the other material. There's always a resistance. This particular component, or this is one particular parameter which is extremely important when we are moved towards the nanoscale, or even if we try to make any nano composite. That means probably if you are not aware, there's a one very popular and very widely considered to be uh, excellent, let us say, finding is a one nanofluid or nano composite from the viewpoint of thermal management. There you simply add a small percentage of a solid to a liquid and we can significantly increase its thermal conductivity. However, there is a one challenge there is that the nanomaterials, whatever you can add, either it's a graphene or some other copper nanoparticles or anything, the one biggest issue, or at least one of the factor that plays the, or that controls or that influences the conductivity is the boundary resistance between the your nanoparticle and the liquid or the matrix. It could be a solid also that is connecting. So think in this particular fashion. So the heat has to travel from your matrix, that could be liquid or a solid, to a highly conductive nanoparticle. So we want to ensure, we want to increase the thermal conductivity of a liquid or a solid whose conductivity is smaller. So to do that one, we're adding another small nanomaterial whose conductivity is significantly higher. So by adding such type of particle there, what do we want to do is, in ideal case, heat has to efficiently travel from your low conducting material to, to the high conducting material, and then from the high conducting material to the low conducting material. So if there is a boundary resistance here, which is significant, then although we add some quantity of nanoparticle which has high thermal conductivity, the end result may not reflect on the overall thermal conductivity of the nanocomposite. There are few ways that people want to try to control that boundary resistance that is still actively pursued by several groups. It's just I want to tell some small information concerning the heat transport through the materials. Okay, guys, that's all from my side for today. We'll again meet in the next class.
So one doubt.
Yep.
Sir. Yeah.
So having the ground boundary, grain boundaries will it reduce the thermal conductivity or
Yeah.
will it
It
increase?
will reduce.
Okay. Okay. So thank you.
Yeah, and also, just if you might find it fascinating, your thermal conductivity, whatever we are measuring, is commonly for a bulk material. The moment you cut your material to the nanoscale, once your mean free path length of the heat conduction comes into picture. Okay, so once your dimensions become smaller and smaller, so your phonons will hit the other boundary, so your conductivity will be significantly small. Okay.
Hello, sir.
That is the story in the solids. Okay. Yeah, designing the materials with high thermal conductivity is a quite active field in both from the viewpoint of electronics, making from the semiconductor viewpoint to the even the management of batteries. In all these fields, one, people try to use the what is already there, and two, people try to synthesize them also. Okay. Anyhow, guys, that's all from my side today. Okay, so we'll again meet with another experiment in the next class.
Hello, sir.
Yep.
Sir, shall I create Google form and collect the all PDFs?
Yeah, exactly. Okay.
Yeah. Okay.
Regarding those details, we can talk with each other later. Okay.
Okay. Okay, sir. Okay, sir.
Okay, guys. We'll meet next week.